Fine. So this is the last class we talked about basically that work done by the conservative force would be simply change of potential energy, and we discussed about the conservative force, right? Conservative force is that force which is basically independent of the path, it doesn't depend on the path, whereas the non-conservative force actually depend on the path. So that means if you change the path, your work done will be different for the different path. And we said that the frictional force actually the non-conservative force, whereas gravitational force actually the conservative force. So that's why when you write down work done by the conservative force would be simply change of potential energy of the system, and we write the work done by the non-conservative force is simply change of mechanical energy, right? And as a result, look at this. If you write down the total work done, you can also write down net work done would be work done by the conservative force plus work done by the non-conservative force, which is simply total change of mechanical energy. You can write also that way. Sometimes we need to do that one actually. If you want to write, you can also write down in that way. We'll do that on later part. Fine. Now let's talk about that potential energy or gravitational potential energy, I should say. Gravitational potential energy. How do we define the gravitational potential energy? Can anyone tell me? What is the definition of the potential energy? Can anyone tell me what should be the potential energy of a system? Let's say I have a system which has a mass m. If I drag that one from this point to this point in vertical direction, which has a height h, then you define the potential energy of this system is mgh, right? Now what if, let's say instead of this vertical direction, if I drag this object from here to here, from let's say point A to B, then what should be its potential energy also in the point B?
0.
Potential energy is 0. Is there any other answer over here? If you say the potential energy is 0, that should be wrong actually. So potential energy couldn't be 0 over here. You can say that if you say the change of the potential energy is equal to the 0, then I will accept your answer, others not. Because when the system has that point, whatever the potential energy over here, it is also the same over here. Now let's say it has the 2 joule over here and there is also the 2 joule, then you can say the change of potential energy is 0. But the system doesn't have ultimately no potential energy. If you say the 0 means there is no potential energy over here, right? The change of the potential energy is simply we write the potential energy final UF minus UI. You say the potential energy is 0 because your logic could be in that case the height is 0, right? That's why you are saying that the potential energy is 0.
Yes, sir.
Yeah, I know that one. So that's why you are saying the potential energy is 0, but that's the wrong concept. It's a very wrong concept. If you define the potential energy of a system is mgh, is a very special case, a very special case. That's not the general definition of the potential energy. General definition of the potential energy is say that, try to understand, I'm going to give you the official definition of the potential energy of a system. Let's say you have a point mass. If you drag this point mass in a gravitational field and you drag from infinity to a particular point, then whatever the work done you have to do to carry this point mass from one point to another point inside a gravitational field, the amount of work done should be the potential energy of this system. I'm saying you again, the amount of work done you have to do to carry a point mass from one point to another point inside a gravitational field, that work done is actually the potential energy of a system. It means that, let's say, you understand the gravitational field, which is simply idea is same, electric potential energy, because if you know that if you keep a point charge, that will create an influence around itself in a region, right? That we define actually the electrostatic field. Now, is same true if you keep a mass over here m and that mass will also create an influence around itself, some location around a region actually. That region we can consider it has a gravitational field over there. Now when we create this gravitational field, inside a gravitational field, if you carry this point mass from infinity to a particular point, let's say this is the point P, whatever the work done you have to do to carry this point mass from infinity to that point or one point to another point inside a gravitational field, that amount of work done would be potential energy of this system. Why? If you ask me, because if you don't have the potential energy, then you will be not able to do that work. So that's mean when you're going to do some work, you have to pay something to perform that work, and you are paying in terms of your potential energy. That's why you said the potential energy or the gravitational potential energy of a system. This is also true for electrostatic potential energy. Same thing, inside a electrical field, if you carry a point charge from one point to another point, whatever the work done you have to do to carry that point charge, that would be also the electric potential energy that we define in the case of electricity of magnetism. But right now, this is the case actually. We have to define the potential energy. The amount of work done I have to do carry a point mass inside a gravitational field from one point to another point. That's why we define actually that gravitational potential energy, right? Although we define the potential energy actually the MGAs, that's not the general definition. That's a very special case. We'll show you that one, how is going to find out that one actually. But before that, we are going to find out this potential energy of this system, general potential energy. If you can find out the general potential energy of a system, then you will be able to find out that special case, which you know that one, right? You understand this part? How are you going to find out the potential energy? The official definition is say that if you want to carry a point mass from one point to another point inside a gravitational field, whatever the work done you have to do to carry this point mass, that work done should be the potential energy of this system. So that means I have to find out how much work will be done if you carry this point mass from one point to another point. That work done would be basically the potential energy of a system. Why? Because when the work is going to be done, you have to pay something, and you are paying in terms of potential energy. We'll find out that part actually initially. All right, let's consider. Excuse me. Let's consider I keep a planet over here which has a mass is m, is going to create a influence over here, or it will create a magnetic gravitational field, and into that gravitational field I'm going to carry this point mass m from infinity to a particular point. Let's say this is the point I'm taking over here, which is the P, and which is at a distance r from this bigger mass. All right, the idea is very simple. I'm dragging this one actually. If I drag, then due to that dragging there will be some work done actually over here. Then what should be that work done? I'm going to find out that part over here. Fine. To find out that work done, what I'm going to do, since this position of this point mass at different time, it will be different, right? On every single second, this would be the position of this point mass. So that's mean this x is changing in every time. That's why I can say this is a variable force. This is also moving. You can say these two masses is going to be attract each other. So that's why it is moving actually. You can say in another way, and that's why this force is actually that variable force. If it is a variable force, then work done by this force actually, if I want to find out, then I have to integrate. I'm going to integrate. This is my integration limit. I'm coming from infinity to the r, and this is my force, and this is the displacement. All right. So now I'm going to plug in this part. So this force is, I know that it should be G capital M smaller m over x square at any second. This is the two mass, which is I am writing the gravitational force actually between the two mass, bigger m and the smaller m, where G is actually universal constant, you know that one, and this is going to be the dx right now, right? Now, if you do that integration part over here, what's going to happen, because these capital G, capital M and small m are constant, so that's why factor out is going to be that infinity to r 1 over x square into dx, right? If you integrate 1 over x square, what it will give you? If I integrate 1 over x square, what it will give me? Can you tell me?
So minus 3 by x.
Minus 3 by x.
No, no. 1 by minus 1
Minus
by
1 by
x.
x, right? So infinity to r actually, because it is x to the power n formula, so it should be x to the power n plus 1 divided by n plus 1 and it is going to be the minus 2 over here. Alright, so then if I want to plug in this value or limiting value, it should be minus 1 over r plus 1 over infinity, right? Because I give the plus sign, because this minus and I multiply over there, it should supposed to be 1 over r minus 1 over infinity, but there is a minus sign, so I multiply that one at a time. So that's why it's become minus 1 by r plus 1 over infinity. Now what is 1 over infinity?
0.
This is 0, right? Then I'll find out this should be the work done. So gm minus gm over r, which means that if you carry this point mass from infinity, this is my point mass, infinity to that point P, which is at a distance r from this bigger mass m, then that amount of work done you have to do. And this would be also the potential energy of this system. This is the official definition of the potential energy, the amount of work done. I'm saying, which is W, is going to be the minus G capital M small r m over r. That is the potential energy of this system. And now we can say another way actually. I'll come over here and explain one more thing. Why is minus sign over here? Let's say if I keep 2 point mass m1 and m2 at a distance r12, then the potential energy between these 2 point mass would be also minus G m1 m2 divided by r12. That's the potential energy we define, the gravitational potential energy of a system. Now this minus sign actually telling you you will lose some energy. When you're going to do some work, you are going to lose some your potential energy, internal energy actually. That's the significance of this minus sign actually. And that's happened actually, and that's when you are going to destroy your potential energy. When you do some work, you become tired, or when you run, you become tired because you are using your internal storage potential energy. That's why you become tired, right? That's the significance of this minus sign. This minus sign telling you the gravity actually everything attract towards its center. It attract towards the center, then it will be actually the lowest energy level. If it is the lowest energy level, then it has to do the minimum amount of work. And by nature, every system actually wants to do the minimum amount of work. Why? Because in that case, it don't has to lose this potential energy, and no one want actually to lose your potential energy, lose its own potential energy. So that's why. So when you drop something, everything is going to towards the center of the earth. Then in that case, it has to do also minimum amount of work. It wants to go to the center of the earth. Then it will be at the lowest energy level. Then it has to do the minimum amount of work, or it has to lose the least potential energy. That's why when you going to find out that potential energy for between the 2 point mass, which is at a distance r, or r1 r2 you can say, then it has also that potential energy which we find out minus G m1 plus m2 divided by r12. Then if you say, that's why I asking you, if I take this mass from here to here, you cannot say the potential energy is 0. It has that amount of potential energy. But if you say the change of the potential energy, that's going to be the 0. Right? Because this is this one potential energy at that point, this one also has the potential energy at that point. If you take the minus of this one, this will be minus, then formula minus, it has the minus, is going to the plus, is going to the plus G m1 m2 divided by r12, that will be cancel out. Then we can say the change of the potential energy is 0, but the total potential energy is not 0 when you also dragging a point mass from one point to another point. It doesn't care about whether you move to the horizontal direction or the vertical direction. All right, that's how we will define the potential energy of this one. Remember, so that's mean if you have 2-point mass between this point which has a distance r12, then the potential energy of this system would be always minus G m1 m2 divided by r12. I can say another way, if I want to arrange these 2-point mass in such a way that they are at a distance r12, then this system has required this amount of work. Right? Sometimes they can ask you how much work you have to do to carry this point mass from one point to this point. Then it means that they are asking to find out the potential energy of that system. Now, let's say what will happen if I carry the third mass over here, m3, which is at a distance over here r13, and this is the distance between r23. Then how much work it has to require to arrange this 3-point mass in such a way? Or I can say another way, what should be the potential energy of these 3 masses if I want to arrange look like that? Alright, so I can write in that case actually, I'll give you that in terms of definition actually, try to understand. Let's say this is space, because potential energy is simply the amount of work done, right? Let's say this is the region I try to indicate over here, which is completely free. There is nothing over here, there is no bigger mass. If there is no mass, there will be no gravitational field, am I right? If there is no charge, there is no electric field. If there is no masses over here, there will be no gravitational field. This means it's completely free space. If it is the free space, in that free space, if I want to carry this m1 mass from infinity to that point, then how much work it has to do over here? What should be the work done? If you want to carry a point mass in a free space, how much work it has to do? Can anyone tell me? In the free space, if you want to carry something from one point to another point, do you have to pay anything or do you have to do any work over there? There will be no work done. Work done will be 0 because there is no field. It doesn't require any do something over here. It can freely move actually. That's why in the free space system can freely move. If there is nothing over here, then it doesn't have to do any work. That's why there will be no work done for this mass over here, m1, or there will be, you can say in that case, it's a potential energy will be basically the 0 over here for this one. Fine. Now, let's say in presence of this m1, if I carry this m2 mass at a distance r12, right now this m1 will create a gravitational field for this m2, right? It will create an influence around a region. That means it will create a gravitational field. Into that gravitational field, you are dragging this m2 right now. Then it has to do some work. That amount of work done is simply the potential energy between these 2 point mass, which is u12. I'll write G m1 plus m2 divided by r12, right? Fine. Now, in presence of these 2 masses m1 and m2, I'm going to drag this mass m3, which is at a distance would be over here. Let's say this is r13 and this is r23. Now, when you're going to drag this m3 alone, then it has to do 2 work. One work for gravitational field for this m1 and another work for this gravitational field is going to be created by this m2. Right? Separately if you think about, but at a result it will give you a resultant gravitational field provided by the m1 and m2. I'll find out that individually for these cases. That means when I'm going to find out the potential energy for this U3 charge, I have to find out the potential energy between U13 plus the potential energy between U23. Am I right? Do you understand my point over here? Fine. So in that case, U3 would be simply U13 means I will write the minus G M1 M3 divided by R13 minus G M2 M3 divided by R23. That should be the potential energy only for the M3. So that's mean in presence of M1 and M2, if you carry this third mass M3, then this amount of work done you have to do, which is actually the would be also the potential energy for U3. Now, if you ask me for what should be the total potential energy for these three masses, if you want to arrange these three masses in such a way, then the total potential energy will be simply the sum of these two. If I write that total potential energy, it should be potential energy between 1 and 2 plus the potential energy for 3, because the potential energy for 1 is doesn't make any sense, because it has the potential energy is 0 in a free space when you carry in absence of any masses. That's why the total potential energy would be simply sum of these two, right? You will find out that part. I'm going to write in this one, which would be U is in that case is going to be minus G M1 M2 divided by R12 minus G M1 M3 divided by R13 minus G M2 M3 divided by R23. So that should be the total potential energy of this system.
Sir,
Yes.
U3 equal মানে সবার উপরের যে লাইনটা ওটা যোগ কেন হলো একটু আরেকবার বলবেন?
Because when you carry this third mass in presence of 1 and 2, then you have to do the two work. One will be work done will be created by this M1, because this M1 will be create a gravitational field, as well as this M2 will be also create a gravitational field, right? Because it has mass, it will create some influence. So that's mean when you carry this M3, at the same time you are carrying the gravitational field, which is the contribution of mass M1 and M2. I cannot find out at a time. So what I did, I'm going to find out this separately. I'm finding out the work done for 1 and 3, which is that gravitational field going to be created by that mass 1. In that field, I'm dragging that mass 3. And second time, the gravitational field going to create by the mass M2. In that field, I'm also dragging that M3. So that's why I'm going to add them together. You understand my part?
স্যার এখানে তো মানে তিনটা যে ইয়া আছে এম এর ভ্যালু আছে, মানে এম গুলা তো সবগুলা মানে প্লেন হিসেবে না, মানে এইচ তো সবগুলাতেই জিরো, তাই না?
H, yeah, I'm moving in the horizontal plane, not the vertical plane.
ওকে।
It will be same if you say instead of drag moving, I can move this way. It's also same. This is the general potential definition. I'm telling you. The formula actually you use U equal to mgh. That's very special case actually, because that one you say that when I'm dragging from here to here, you say the potential energy actually is zero, according to this formula, right? Because your logic is right. You say that since h is zero, so potential energy would be zero according to this law or this formula. But that's not true. I show you over here. That means this is formula is a very special case. Very special case. We cannot always use this one. We can use, there is a particular case, I will come to that part. But interesting thing that this formula is came from that one. I'll show you that one. Let's keep in that one. Let's say we write the potential energy general formula we are going to write, which is actually that U actually that minus G capital M smaller m over r. That means these two mass at a distance r, then that should be the potential energy. All right. Let's say I have this planet, which is our planet Earth, mass is m and the radius is r. I keep a point mass over here, which is smaller mass at a height actually that h, right? It's not too far away actually, because my drawing is doesn't look like, but I try to show that. So one more thing I want to say you, what should be the potential energy if I goes to the infinity? What should be the potential energy if I goes to the infinity? That means if r goes to infinity, then what should be the value of the u?
0.
It should be 0, right? It should be 0. So remember, the potential energy of this system is going to be, that's when if you are far away from this r, very far away, then the potential energy would be 0, because r is in that case going to be that infinite, right? It's going to be the 0. Fine. So I know if I keep that mass at a height h, then I'm going to say that this u should be, by definition, it should be minus g capital M smaller m over r plus h. Can you write? That should be the potential energy between these two masses according to the general definition, right? Fine. I know one thing actually over here, what this two has also a force. That force you can write, it should be also I'm going to write this would be the g capital M smaller m over r plus h square, right? And this thing I'm going to say that this one would be also, I can write mg equal to that g capital M smaller m over r plus h square. Can you write? Because from the Newton's second law, I write actually that F equal to ma, which is the acceleration. But since I'm considering about the gravity, I use the acceleration as a z over here, which is the acceleration due to the gravity. Then I can neglect this part, and we say that this g would be simply gm over r plus h square. That's the general formula to find out the acceleration due to the gravity for any planet. And in general, we know that this height is very small, because if you keep it, let's say if you keep that at a height 2 meter or 3 meter, which is very small with respect to the r is 6,400 kilometer, right? With respect to that, 2 meter or 3 meter or 5 meter is negligible. It doesn't have any contribution. So that's why if r is much greater than h, then we can write g would be simply gm over r square, right? So that's the general formula to find out the acceleration due to the gravity in any planet system. And look at this, this is very interesting. This is independent of the object. It doesn't care about whether you fall a bigger mass or a smaller mass, they will fall at the same rate of the acceleration because of this equation. This equation is the g is constant, this is the mass of that your planet, and this is the radius of your planet. In that planet you are observing that experiment or doing that experiment. So that's mean the gravitational acceleration is simply depend on that planet, in which planet you are doing that experiment, which is the mass of this planet, and this is the radius of this planet also. So that's why using this formula you will be able to find out that the acceleration due to gravity for any planet if you just know the mass and the radius. All right, I'll use this formula right now. Look at this. Fine. So now look at this. Can I write down this formula in that way? It should be minus g capital M smaller m over, let's say I'm going to factor out this r. It should be r plus h by r. Can you write this one? I just factor out this r. If you multiply, sorry, it should be 1. I'm sorry. Obviously, it's going to be the 1 because I just factor out this r from these two quantity, and it should be the r. If you multiply this r plus r h over r, you will find out exactly the same equation. All right, I'm going to do some mathematics over here. Let's write down minus g capital M smaller m over r into this one. I'm going to write 1 plus h over r into 1 inverse. Can I write this one? Right? It's the same thing actually. This one and this line is the same. Now what I'm going to do, I'm going to expand this one by using the binomial expansion for this one, and I also neglect the higher term or Maclaurin series, you know that. So it should be 1 minus h over r, and I also neglect that higher part, right? You know that one. Probably, let's say if you have a series a plus x to the power n, then what we did, we write down a to the power n plus nx plus dot dot, right? N minus 1 divided by 2 into x square. That actually the higher term. I neglect that part actually. I write up to that one because my n is actually the minus 1. So that's why I write down the a to the power n, which would be 1 over minus 1, which would be simply the 1 over 1, which will give you the 1 minus nx. This one I'll find out that part, right? Is that okay? Fine. Now this one should be, you should be minus g capital M smaller m over r. I just multiply with this quantity with that one. This will be minus 1 plus over here it should be g capital M smaller m h divided by r square, if we just multiply with that one. Now what is this? G m over r square. This is small g we write over here, right? Then we can write this formula, g would be, or u would be minus g capital M smaller m over r plus mgh, right? Because you replace this part actually by the g. Then when you say the potential energy of a system at the surface of the earth, you write down mgh. In that case you neglect this contribution, which is wrong actually, right? In a bigger scale you cannot neglect this part, but in a small scale you can do that one, because when we are doing this experiment we are very close to the earth. We are very close to the earth. That's why we are using that formula, the potential energy U actually mgh is a very special case. We can do only this one if we do the experiment in a surface of the earth. But if you consider, let's say you have that object and you keep a mass into the space station, then you cannot say that you cannot neglect this part. You cannot use this formula to find out the potential energy mgh. In that case you have to use that formula.
Sir?
Yeah.
তখন এন জি প্রাইম ইউজ করা যাবে না? জি প্রাইম
G prime.
জি প্রাইম হ্যাঁ, মানে চেঞ্জ ইন জি, চেঞ্জ ইন গ্র্যাভিটেশন ডিউ টু মানে গ্র্যাভিটি ডিউ টু অ্যাক্সিলারেশন।
So then you have to know the potential energy of this one, right?
হ্যাঁ।
Why do you going to find out that change in G actually, or change in U actually, gravitational potential energy?
চেঞ্জ ইন জি ছিল না 11 12 এ আমরা চেঞ্জ ইন জি বের করতাম হাইটের জন্য। ওই নিউ জি যেটা মানে জি যেটা একটা বের হবে ওটা জাস্ট বসে দিলে এটা আসা যাওয়ার কথা।
No, no. That's what I'm saying, that this is the formula is very close to the earth surface because you neglect that part. All right, but you can use that formula u actually minus g capital M smaller m over r is always is going to do the work for you to find out the potential energy between any 2 points, whether you move to the vertical direction, whether you move to the horizontal direction, or whether you meet in any direction, you'll be able to find out this one. All right, that's why I'm saying that this is actually the general formula to find out the potential energy between the two mass. If the mass are at a distance r, then there should be the potential energy, and this one is a very special case. We can use only that part for a short distance. If we do any experiment very close or precisely, you can say that on the surface of the earth, then you are able to use this equation, otherwise not. In a long picture you cannot use this formula to find out the potential energy of a system. It will give you the wrong answer actually. All right, let's talk about another case actually. There's a case actually, you say that actually that let's say if I take that gradient of this one du over dr, what it will give me? Capital R, I can write this one. because r is capital R over here. What will give me? Can you tell me if I take the derivative of this function with respect to the r?
The GMM by R square.
G m by r square, right? Which is simply
Huh.
the force. It's a gravitational force actually. All right. So that's why there is a relation between that gravitational force and the potential energy is the negative grad of potential is called the grad of potential. That means if you know the potential energy, you will be able to find out the force, or vice versa. If you know the force, you'll be able to also find out the potential energy from here. Because I can find out this del u, it should be minus f into dr, right? I just take the cross product over here. Then if I integrate this one, I'll find out simply it should be u or del u, because there is limiting value over here, u1 minus u2, it should be del u, it should be minus, let's say, r1 to r2 f into dr. Using that formula, we'll be also able to find out that potential energy of a system. And that's why we say that this is also definition of the work done, right? Force into displacement. And that's why we say that this is del u actually the minus the del w. And that's why I'm saying that in the case work done by the conservative force is simply change of potential energy. And this equation is not a new for you. You probably use in the thermodynamics case. And I'm saying that when you're going to do some work, definitely you have to pay something. You're paying in terms of potential energy, which is the u over here. And I'm saying that, let's say, I'm going to show you, I have that spring force minus kx, right? If I want to find out the potential energy of this spring if I want to find out the potential energy for a spring, then what I'm going to do, I'm going to use this one actually. It should be simply del u, or u, whatever you write down, del u. It should be minus, this minus, and formula minus is going to plus over here, right? It should be start from the 0 to x basically, and it should be k into x into dx, right? I'm just replace f by the kx, and it is a displacement is the x, so that's I write down instead of r, I write down the x over here. Then you will find out this potential energy for the spring is going to be, what should be that? If you integrate kx, k is constant, if you factor out the outside, it should be simply
6 square by 2.
x square by 2. Then I'll find out it should be half of kx square. That's also the potential energy of a spring, right? So that's mean if I know the force, I'll be able to find out the potential energy of a system, or vice versa. If you take the derivative of this function with respect to x, you will find out that force. That's why it is saying that it's a grad of potential of this system. That's also true for electrostatic case. We can write down it's a negative grad of potential. If you take that gradient of that potential, you will find out that force of a system. And this minus sign actually, they tell you gravitational force is always push the system to goes to the lowest energy level. That's why if you drop something, instead of moving to the other direction, it always falls to the downward direction. Why? Because gravitational force attract all the system towards its center. In that case, the gravity has to do the minimum amount of work if it is the system is in the lowest energy level. Everything, if you release, it will try to go to the center of this earth, or center of the planet actually, because in that case the planet has to do the minimum amount of work. If it goes to the center, then it will be in the actually the lowest energy level. Then definitely it has to do the minimum amount of work. That's why that everything falls to the downward because of this minus sign. The gravitational force always pushes the system to goes to the lowest energy level. All right, is there any question over here? So we find out this potential energy actually that half of kx square, right? What would be its curve if I draw this curve? Let's say potential energy versus x. What should be this curve look like? What should be this curve look like? Can anyone tell me? What this curve should be look like? Come on guys, it's a y equal to x square curve because this is a constant.
It's a parabola.
It's a parabola, obviously. Right, so that's when using this curve actually you can also find out that the system. What about
সেটা হাফ প্যারাবোলা হলো কেন?
No, it's a total.
মাইনাস নাই দেখে।
Yeah. If you take in the negative direction, you will also find out that part. What about gravitational potential energy? If you use that part, actually, you actually that mgh. What should be that curve of this potential energy?
স্ট্রেট লাইন থেকে
Yeah,
স্ট্রেট লাইন পাসিং থ্রু অরিজিন
yeah. So if you say this is actually the h, this is actually u, it should be straight line passing through the origin. Right. What about this one? Minus g capital M smaller m over r is the general potential energy. What should be this potential energy look like? Let's say this is my r, this is my potential energy. In that case, it would be 1 over r. So closest to look like that. Asymptotic actually. It's coming from that one point. Is going to the. It's a negative because I draw in the negative region. That's why it goes to the infinity. I do not know what will happen actually at the infinity. It could be the 0. If it is can reach the infinity. All right. That's how actually we can correlate this potential energy of this system. Means that's how. Is there any question over here? Fine, let's do that some problem over here. First of all, try to do. I have a system like that. Give me one moment. Okay, this is the one I'm looking for. Alright, let's say I have inclined plane. To the inclined plane is the angle theta. There is a mass over here, which is a mass is m. 1 minute, guys. My chairperson has given me a call. Tom, sir. Hello. Sir, আমি ক্লাস নিচ্ছি স্যার। জি স্যার, অনলাইন ক্লাস। জি স্যার। আচ্ছা আচ্ছা, না স্যার, আমি ক্লাস শেষ করে ফোন দেবো আপনি। ওকে স্যার, সালাম স্যার। Alright, guys, can you hear me, right? So, hello, can you hear me?
Yes, sir.
Alright, please respond, guys, otherwise I will not understand. Let's say this is that block has a mass actually that 10 kg, and it's start with the initial velocity which is vi. It's moving actually 15 meter per second. At that moment I apply a force over here which is that 100 Newton. This applied force actually that 100 Newton, and the coefficient of kinetic friction since it's moving is 0.4, and the angle theta is given is 20 degree. Then they asked to find out a lot of thing over here. First question, find out the work done by the gravity. Second question, how much work or how much energy will be lost by the friction is the second question. So that's when it is going to calculate the work done by the frictional force, because that amount of work or energy will be the loss from the system. When friction is going to do the some work, it will lose that amount of work energy from the system. Number 3, what is the work done by the applied force? Number 4, they ask you what is the change of kinetic energy? And number 5, they ask you what should be the velocity of the block after traveling this distance. This distance is, let's say, distance is a 5 meter. This distance is 5 meter. After traveling, what should be the speed of this block also overhead? Alright, to solve this one, I need to draw the free body diagram. I'm going to draw that one. So if I draw the free body diagram, I'll find out this would be my mg, this would be my normal reaction force, this would be my mg cos theta, this would be my mg sin theta, this is my applied force, and there will be one more force actually, that frictional force over here, right? Kinetic frictional force, because it's moving. Alright, so remember, when you're going to find out that net work done of a system, always you have to find out the work done by the for every single force acting on the system, and that you have to find out over. In that case, if you want to find out the net work done of a system, first of all, first question they ask you to find out the work done by the gravitational force. I know the gravitational force actually that mg, but I find out some component of the gravitational force which is mg sin theta. Actually, this mg sin theta is going to do the work. You can do in both way. If I write down that formula F into D, I'll simply write down, if you write down mg, then you have to find out also this angle over here, right? So which angle would be theta plus 90, right? Or I can write down mg sin theta. Mg sin theta, this is my force, this is the displacement, and what is the angle between this mg sin theta and the D? Mg sin theta actually the downward and D is the upward, which means this angle is 180 degree over here. Then I'll write this would be cos of 180 degree. Mg sin theta actually my force over here, because I'm taking that gravitational force which is actually doing the work over here. Then if you plug in those part, you will be find out this would be mg sin 20 degree, angle is 20 degree, right, into the D, and cos of 180 degree is simply the -1. That means the work done by this gravitational force would be simply minus mgd sin 20 degree. So that should be actually the work done by the gravitational force. This is the answer. And if you just plug in this value, you will find out your numerical part actually over here. So that would be simply the work done would be minus 167.58 joule. This is the answer of that first question. All right.
Sir, dr value কত?
A dr value is given, which is the 5 meter. That's the D is given here. Thank you. D is actually that 5 meter over here. Alright, now what about the work done by the frictional force? To find out the work done by the frictional force, I'll write down again Fk. So it should be that frictional force into the displacement. So I know this angle between these two vectors is also the 180 degree. I'll write down the Fk into D into cos of 180 degree, or simply I can write the Fk would be a minus Fk into D, and Fk you can find out minus mu k into n into D, right? And that mu k would be n would be simply mu k into mg cos 20 degree into the D. You can find out, because if you look at this picture, n should be definitely mg cosine theta over here. So that's why you can write down this work done by the frictional force would be simply minus.
Sir?
Yep.
স্যার এক নম্বরে এফ তে এমজি সাইন থিটা হলো কেন?
I'll come to that point. the one, look at this. I said you when there will be some work done, there must be some force in the direction of displacement or in the opposite direction of displacement, right? Can you remember that one when I'm giving the definition of the work done at the very beginning of this work energy chapter?
স্যার আরেকবার একটু বললাম।
When there will be some work done, it has to be some force or component of the force in the direction of your displacement or the opposite direction of your displacement.
আচ্ছা
Because you can do it by this one also. In that case, you have to write, uh, if you write down this mg only, this is actually your force, this is the displacement, and what is the angle between these two vector? You have to know that one in that case, which should be this angle plus this angle is theta. It should be 90 degree plus theta actually.
110
Yeah, 110. You will find out the same answer. Alright, so then now if you plug in this value, you will find out the work done by the frictional force, that should be minus 184 joule. And this amount of energy will be lost from the system because of this friction. Friction is going to do some work and that energy will be lost from the system. Alright, then number 3, what is the work done by the applied force? Which is very simple, F into D, and these two vectors are parallel, so it should be Ft cos 0, F is 100, D is 5, is going to be that 500 joule, right? And then what should be that number 4? Number 4 is find out change of kinetic energy. So change of kinetic energy would be simply net work done from the work energy chapter. We can write down work energy theorem, right? We know that net work done on a system, it will be change of kinetic energy. It doesn't care about whether it is a conservative or the non-conservative force, or whether it is a constant or the variable force. Every time we can use this formula actually. Net work done will be simply the change of kinetic energy of that one. Now net work done will be work done by the applied force, work done by the gravitational force, work done by the frictional force, work done by the normal reaction force, right? These are the force actually acting over here. I didn't write down this mg cosine, mg sine, and mg, which is actually the gravitational force. These are the 4 forces over here, right? So that's why I write down this part. But what should be the work done by the normal reaction force?
স্যার mg cos theta cos 90 degree
So then it should be
Into D.
0. Cos 90 actually is 0, right?
হ্যাঁ
So that's why there will be no work done by the normal reaction force over here. That means I'll find out work done or change of kinetic energy, which should be simply work done by these 3 forces over here. So then it will find out this will be, because you know that one everything. If you plug in this part, you will find out that is going to be that 148.5 joule. Right? This is actually that work done or change of kinetic energy of this system. This is the answer of number 4. Number 5. So they asked to find out that final speed of this block. That I can find out. Change of kinetic energy would be kf, or I can write down the half of mvf square. This is the final energy minus half of mvi square. From here I can find out this part, right? Because I know that vi, and I also know the mass. I also know the change of kinetic energy. Then these you can find out from that part. So if you plug in this part, this Vf, it should be, let's do in another way. You can multiply, I'm writing this Vf square is going to be the 2 del k divided by m, right? So then you can find out this final kinetic energy, which is going to be that Vf is going to be simply root over twice del k divided by m. If you plug in those values, you will find out your answer actually. So I do not know that answer actually, I give you from instantly. So whatever the value, you know the del k, you know the mass, you will be able to find out that final velocity.
স্যার 2 নাম্বারটা একটু দেখাবেন আরেকবার
Which
ওয়ার্ক ডান ফ্রিকশনাল ফোর্স ওয়ার্ক ডান ডিউ টু ফ্রিকশনাল ফোর্স
were done by the friction force.
হ্যাঁ
All right. Come on, my system is not responding. Because look at this, for your frictional force actually, uh, this is actually your block which is moving towards the upward direction, but your frictional force is the downward direction, right? This is D and this is Fk. That's why I write down, let's say Fk into D. This is my force, this is my displacement, and this is that angle between these two vectors, cos of 180 degree. Then I also find out Fk value. Fk value would be mu k into n, and it should be mg cosine theta. Theta is 20 degree. I just plug in it over here. Then you just find out this will be the work done by the frictional force. And if you plug in the
সো মানে আমরা cos এর পরের লাইনে cos আবার আসছে সেকেন্ড না না ঠিক আছে বুঝছি n এর জন্য
yes. Alright, let's say I have a track. It's a track over here. Although my drawing is not exactly straight. Has to be. And it's a icy track, which means it's a slippery. There is no friction over here. You consider the frictionless. Then we'll introduce the friction also. Let's say I release a block from there, or also the ball. It is ball. Let's keep it the ball. Then it will be interesting thing. I release that block over here. It's a frictionless. What we are going to do? Actually, let's say this is actually that H1. This is actually that H2. Clearly, this H1 is greater than H2. Since it's a frictionless, it's not going to roll down this ball. It will be only slide over here, which means it has only the translational motion. Right? It will be simply that sliding on the surface. It's not going to roll down over here. To rolling the system, it's required the friction. Since I say it's a frictionless, it will be only skid on that surface. What will happen after coming that point? Let's say this is the point A and this is the point B. What will happen? Can you guys give me some 5 minutes extra? Do you have a class after this? Hello? Hello?
Yes, sir.
Do you have a class after this?
আমার নাই।
Alright, so you have 6 minutes. Let's see whether I can finish for that or not. I need to talk with you. So I can take 5 minutes from you right now? Can I take 5 minutes more?
Yes, sir.
Alright, thank you very much. So if we slide down over here, after coming the point B, will the ball will be stopped over here? What do you think? Will the ball will be stopped over here?
No, sir.
Will be not stopped, right? Because it has greater kinetic energy. Still have that kinetic energy. It will try to move, and it will be simply fly off that surface. And I want to know where it will be strike the ground, and with what velocity it will be strike the ground. All right. So this is called actually the comprehensive problem. Right now, the second part, when is this ball is going to be the fly from the surface, that is actually the projectile motion. You can handle those part, right, easily. And initially, it will be energy conservation law we can use, because there is no frictional force, or there is no non-conservative force present into the system. I can write this: the energy at the point A must be equal to total mechanical energy at the point B, right? because it is simply that conservative system over here. There is no frictional force into over here, which means the change of mechanical energy must be the zero over here. Let's write down what should be the velocity at that point. I'll write down kinetic energy, which let's say I release the system from the rest over here. I release the system from the rest over here. Then I can write the kinetic energy at point A plus the potential energy at point A. That should be the kinetic energy at point B plus the potential energy at point B. The kinetic energy at point A is 0. The potential energy at point A, you can write down the mgh1, that is half of m vv square that we are looking for, plus mgh2. I can cancel this m from both sides. Then I can find out this vv would be simply root over twice g into h1 minus h2, right? You can do that one. If you multiply by the 2, it should be twice g h1. It should be simply vv square plus twice g h2. I can factor out this twice g. It will be simply h1 minus h2. So that's the velocity at the point B. If I know that velocity, then I'll be able to find out that actually that why it's going to be strike, because once it start fly up from the surface, I know it will be moves with a constant velocity or constant acceleration along to the x direction, because I'm going to find out this displacement along to the x direction, right? It will move at a constant velocity along to the x direction. We know that from the kinematics chapter actually. Then that's mean it will move with the same velocity with the vv, because we are neglecting the air friction also. That's mean it would be vv into the t, right? Then I need to know the what is the t over here. T is the time period that's required to fly up from that surface. That I can also find out. To find out the t, I'll write down the formula. Y should be y naught v naught yt plus half of a yt square, right? If I choose, that is my origin. Come on, where? That is my origin over here, which is this point. This is my origin. It's not responding. I'm considering this is my origin over here actually. This is my origin. Then obviously it is moving to the downward direction, which is the h2 over here, right? And in that case, it has no initial velocity.
Sir, origin coefficient
at the top point. At the top point.
তাহলে ফাইনাল হচ্ছে h2 minus h2,
Yes.
আর ইনিশিয়াল y naught হচ্ছে 0 আর v naught yt ও 0.
Yes, exactly, right? Then I can write down this naught would be 0. This is would be 0 over here, right? I'll write down this would be minus h2 equal to minus, I say 9.8 divided by 2 is to be minus 4.9 t square. This will be cancelled out, right? Then I can find out the t from there. So t would be simply h2 divided by 4.9 in the square root. That's with the time. If you know the h2, you can plug in over here to find out the second. Now your displacement of this object is going to be that vv into the t. And what is the vv? Vv, you find out that one, which is root over, or I can write down at a time, it's the root over twice g h2 minus h1 into t is root over h2 divided by 4.9. That's the answer to find out that part where it is going to be strike the ground. If you know that value h1, h2, you will be able to find out that displacement, right? Fine. Now what about the velocity? So velocity we can find out, since it's a two-dimensional, it has a two component. One is vx I hat one is vx I hat plus another is vy z hat, right? Am I right? Because when this one is going to strike the ground, it has a two component. You can see from there, when you distract the ground, you will find out the two component over here. One is actually that Vx, let me use the two another color, this one. Oh come on, my system is disturbing. This will be my Vx and this will be my Vy, right? Alright, then I have to find out these two components. Vx is positive and the Vy would be negative. Alright, so Vx would be what? Vx would be Vv, right? This would be Vv, which should be root over twice g h2 minus h1, right? This is my Vx, and the Vy we are going to find out v0y plus ayt, right? And this v0y actually the 0, and it should be minus ay actually the 9.8 into the t is to find out, which is root over h2 divided by 4.9, right? This is the t. Then you can find out that velocity. So velocity oh come on, it's not working. Alright, so each total velocity is going to be that Vx I hat plus Vy z hat. So Vx is what? You find out that part is a Vv, which is, you can write down root over twice g h2 minus h1 I hat minus 9.8 root over h2 divided by 4.9 z hat. That should be the velocity, right? You can find it in that way. That is the answer of this question. So that's how actually you can do this part. Alright, thank you very much guys for your extra time. Now